So, yeah, thanks for having me. I've actually never been to the grass pod before. I've heard so many things about it, so it's been great to see everything. So I'm here to talk about Generalist humanoid robots. I think that 2025 was probably the year that all these things went mainstream, as you guys like I think more robots. This was the figure humanoid robot, and they've made it the cover of the Time magazine. You can now order a humanoid robot that goes to your home. So I'm here to talk a little bit about like what it was that kind of changed a lot of people's views, including mine, and has made this like really interesting this year, and also what the big problems are that we have to go through. So first of all, so why did all this happening? Why did all this happen, and why is it happening now? And what has changed? I will say there are three things that I've been very excited about that have and that like really have started to allow us to build these robots and get them out in the world. The first one is that we can now really control these robots reliably, and you've all seen probably videos of robots dancing and backflipping and doing crazy jump kicks and things like that. But it's beyond that. There's a lot of other stuff that is necessary fundamentally to be able to deploy robots into different environments, and we'll go over that. That there's just a huge change, especially in like outside of the lab, and how we can actually manage to get enough data and information to train robots and make them useful. And and generally, where like models are getting better and more capable, and you can actually kind of do stuff with them now. Although it's still working on that. So why am I talking about this? Number one, so this is I should say beforehand that all this is like my views, and that we're talking about like not necessarily HLB or anything official. But so I worked in video research for a while. At VLAs, worked on home robots. A lot of the research that I've done in the past has been these are just random papers, but like building generalizable robot skills, making robots that can go around and perform a wide range of different tasks across embodiments with and all this stuff is with no prior models or no prior information. So basically, like, how do we look at how robots, particularly like really how do we look at building systems so that robots can go out into the real world and kind of perform like room complex multi-step tasks, especially in the case where you don't really know, where you don't have any prior information. So now that's so it's stuff like this, like putting like using language commands to have robots that move around, pick up objects. This is the whole robot, so the very lightweight robot, not a humanoid at all. Like move it. So these are all given language instructions that has to explore the house and look around and be able to fix things up based on spatial memory. You can also use these kinds of things for answering, for making the robot, for like having a robot go and explore and search for objects, taking some dynamically build Z graphs so that we could answer questions and interact with the world. Okay, so this is just background. So this is the kind of things that I've worked on before. But the actual, so and then I started at Agility last year. But the actual reason that I am here particularly is that I spend a lot of time writing about robots. It's the IEEE. And then I like as Tony said, I've been spending like a lot of time in the last few years talking to many different researchers and startups about what they're working on, and kind of like, so this is I guess this slide is not my overview of like my current role, but my overview of the industry as a whole, and like what interesting stuff has been happening lately. So we do this all the time. Talk to lots of people. This is the most recent one. This one actually it's not the most recent one. The most recent one today was physical intelligence. So but yeah. So like I said, three big trends from the last year that I think have really influenced kind of my thinking about what the world about kind of the way robotics is looking. So making robots that can stand up and interact with the world reliably, making sure that we actually can generate data. And look, this is a huge issue because roboticists, as I'm sure you all know, have always been data starved. As far as we never have enough information to be able to try like even a computer vision quality level model. So people have really just been trying very hard to solve this problem. And then finally there are these first traces of like how we can do general intelligence and lots of others. And then of course there's so many other outstanding issues still to solve that I hope that all of you have some time to solve later in this year as well. But we'll start off with just talking about like robotic control. So I was at ICRA in Japan, like in last year when they launched this thing. This is the Unity G1. And at the time, all it could do was kind of slowly move around in this kind of very stiff artificial wave. And that was at the time. We were all really blown away by how cheap this was. And still, it's pretty impressive how cheap it is. Because back when I was a grad student, you couldn't like 16K wouldn't buy you half of a robot. But anyway, so this is, so you can take a look at it. So this is, but now where we are, from the end of this, from the end of 2025, so a year later, we have things like this: the robot playing basketball and flipping off walls. These are from this is from the Humanoid recent paper, and this is from Amazon FAR. So the robots have over the course of like about a year and a half, we've gone from like this robot barely able to walk down the street or barely able to walk down the aisle to being able to interact with the environment and sort of like do all these kind of complicated tasks. Particularly, we've been able to move away from these specialized blind skills to being able to interact with the world. So particularly, I think, so the big advantage, but there's still a lot of stuff missing here, especially when it comes to blind skills. So the big advantage of humanoids, in particular, is that it has how well they can act in like very constrained spaces and cover across different types of terrain. They're dynamically stable and are able to use this to their advantage. So like, I should be able to like grab a handle of the fridge and lean back to pull it open the way a human might. So I can be very energy efficient and very safe. I can, to be able to do this, I have to be able to reason both about what's surrounding the robot, what force it's applying, and these are things that generally like we haven't been able to do very well in the past, and then you can't do this very well with the SATCOG either. So to get there, this is one of the core things that we've been looking at is how do you train general purpose robot controllers so that you can have them interacting with it, so that you can collect lots of demonstration data in different environments. So like this also ties into the second part, like how do we actually get robot data to be able to answer questions? But like start out with this is Twist, which is a captain controller that we safely operate the robot to perform a bunch of different tasks. We can handle different perturbations, like for this case that you have the operator here is using a motion capture suit and actually carrying around a box of the person, right? So the fact that you can now like generally control these robots fairly easily, there's like a new launch based on this capability basically every day. I think Westlake just announced their Humanoid, which with a video about that, probably a briefing debate. So there's lots of work in this vein, but this core capability lets us actually have the robot moving around and start. This is sort of how we feel start to actually do stuff in the world. And the way that all these work, as many of you probably know, so like you start out with like an offline human motion data set, train controller, and simulation. Everything is done in Isaac Sim and goes sim to real, because you just can't really do this without reinforcement learning. We tried the other option before. So you use these large polyop data sets, we target it, and then you can try to learn other different types of conditional policies downstream to be able to get them to act in the world. And this is so for example, Twist there is tracking your hands and feet ahead to collect all this demonstration data. So beyond that, the other big trend that I think we've seen a lot of that I like to see is a bringing in perception aware control. So this is one that we talked to the authors of this one recently, half a year ago. But basically, can we have robots that like how do we actually generate video data so that we can interact with the environment and have the robots like they go upstairs and sit down, everything like that. So given this, there's a lot of restrictions on what kinds of data are useful for collecting these things. Particularly, like we need to be able to I think that they originally wanted to be able to bring in a YouTube video to teach the robots, and of course that is not what happens. Every video is very carefully curated and arranged to make sure that you can actually load it into the simulation and create a 3D mesh. But like the pieces are starting to come into place where you can actually start to get the robots do this. The other thing is that right now a lot of these policies that we see before, like particularly like these whole body control policies, don't really allow you to go through and deal with different environmental geometry. So I think that this is so one thing is that we still don't see a lot of, particularly in combination with manipulation, is that there's this like how do we manage to get robots that can get that and both that can now perceive the environment and respond to it quickly enough that they can move across different types of terrain. And this is from into, but there's a few different papers on this. Basically, what this is doing is that it takes in and it builds an attention-based map, and then you can learn fully neural. So it's taking that in. So its attention is all you need, but for locomotion is what they pitched it. And finally, the other big thing that we've been seeing for whole body robot robot control here is force control. So I think that force control is something that is often kind of overlooked for robots. Like generally speaking, if you look at robot policies that we have seen in the real world, like they tend to be very stiff, they tend to be very slow moving, and they don't make much contact with the environment. And that actually makes a huge difference if you're trying to do something like this. So in this case, like you're trying to wipe off a whiteboard here, that involves consistently applying a reasonable amount of force as the robot moves its hand across the board. And there are so many tasks like this. They're like for peg and hold tasks or insertion tasks are a huge part of a lot of industrial manipulation. They're like, you need them out. You need to be able to do a lot of tasks in the real world. Like I said, like the big advantage of humanoids, the way that humans interact with stuff is that we are constantly manipulating our whole body to apply force to stuff. Like opening a door, you don't just stand stationary and pull your arm back. You use your whole body. And so there's still fairly little work on this. This is like, for this one, this is UniFP from GLO, but like, so then there's also Falcon, I think, there's another one that I didn't include the video. But basically, the changes that there are some initial promising signs that you can in fact train these sorts of whole body controllers that do apply specific amounts of force, and you can see it does make a visible difference when trying to do something like clean off this whiteboard. So that unlocks a very wide range of tasks that you just can't do with like an earlier controller, like any of these, right? Like if we go back to this one, because you can see how clumsy the motions are in a case like this, where because it can't control exactly how it's going to interact with the environment, it can't apply the right amount of force, and it can't motion anything. So, okay, so these are the promising signs for like. So now we have at the same time, this allows for us to be we have these RL-based control stacks. Everything is trained in simulation now. That's the state of the art here. There's, as far as I know, no training in the real world for any of these major works. But we have robots that can move around the environment. There's some pieces that allow us to avoid obstacles and take in data from different sources. And finally, to be able to exert forces on their environment to be able to perform these different tasks. Okay, so at substantial progress, nothing has been brought together. Like we're still not doing like mobile manipulation. We're certainly not able to like have a robot walk around your home and do any of these things, like where there's actual objects right next to you that you might run into. So I think we're still quite far away from being able to do complex manipulation on these things. But at the very least, like you can see the pieces that seem to all be very fundamental and necessary to be able to do the kinds of things that would make a human and robot in any way useful, right? Okay, so basically that's the case for optimism on the body side. Like this is why I think like, okay, so we've got a few of these pieces that are driving in the right direction. So now let's talk about data. So as I said, so the big thing with robot data is that there's not very much of it, especially if you want to try to compare it to any of the other field of AI or machine learning. So like this is an example that I liked. This is from a talk by Ken Goldberg, where Pi has Pi for Pi 0 collected 10,000 hours of robot data. There's other ones since then that have collected 10 or 20,000 hours, but like 2.5, which is that was a good model, not a modern model, not a very big model, had about the equivalent of 100,000 years worth of data, 1.2 billion hours equivalent in token. So like basically, there's a massive amount of difference between the amount of data that we use for most other types of models that give actual general purpose performance. And so we have to come up with a lot of different creative ways of closing that gap if we want general purpose robot models under the same paradigm as we've seen for a lot of things. So where are we going to get all this information? There are three different, I'll give you a rundown of three different things. Obviously, we can do teleoperation for all of this and to slowly scale robots out into the world. That has its own issues, particularly since this is teleoperation data is slow and it's expensive and it requires you to have robots out there doing interesting things, which creates other issues downstream because, okay, but like, which we'll get to as we go through this list. But yeah, so the three options that I'm going to go through, like people have been spending a lot of time over the last year. The big research trend is basically a lot of it is just figuring out how to get data out there that's cheap and scalable and easy for robots so that we can start to be in the same regime as other fields of AI. Okay, so the first one that has been very buzzy lately, of course, is learning from egocentric human video. So learning from egocentric human video is we'll see more. This will come up again. It's a big theme I think from research in the last year. Is that it allows you to it allows you to very quickly scale human data because all you need to do is wear something like a pair of various glasses. So this is from Ego. This is from Ego Mimic, or Emma. Sorry, this is from Emma. Different, not Ego Mimic. But so that basically the core insight is if you haven't tried to collect mobile manipulation data, if you're interested in mobile manipulation, which I think you all should be because it's a very interesting robotics problem, and you try to collect demonstration data using for mobile manipulation, it's excruciating. It takes a really, really long time to get basically anywhere because you have this robot that you've got that you can not only you can't just like sit there and collect the right example over and over again. You're moving this robot around, so your cycle to complete a task can be 5 or 10 minutes. So for like a very small amount of data, and that means that you end up really just like you just can't even get close to a useful amount of data to train a modern policy or even fine-tune one, right? So, okay, so that's that. So what we see people doing instead is using egocentric human data for this. So you can, especially with something like the area glasses, you can get the accurate pose of the robot wherever it is in the world and move around. You can, and then that lets you get human trajectory data, and then you can sort of retarget it, then apply it to a robot. And this is kind of what the human video looks like. So it's still not super natural human video. It's like you're holding it the way that you would if you were a robot, and still it's better than nothing. That's a common theme across a lot of this. So we're still definitely not at the point where you can just trivially drop in human data. That definitely is not working yet. So fortunately, the other thing is that it does, like after some retargeting for the trajectory, it doesn't require a ton of work. Like you don't need to collect they don't need to collect human data in the new scene to get all this to work. You can just use the robot data or the egocentric human data. There's been other work as well recently that have looked at basically you can just throw these different data sets together, and as models get big enough and the data sets get big enough, it will learn the commonalities between them, and you then just kind of co-train on these different modalities to get data performance. This is important for both for cost and for making it easy to scale the data quickly. But the most valuable thing about this is just that you can leverage very large amounts of much easier data than we have before, than that has ever really been built before. And this is from Georgia Tech and his students. Okay, so like egocentric data lets us learn some things. But it's not. It's great for pick and place and for simple tasks, which fortunately is a lot of what people test on for these kinds of models right now, for vision language action models. It is not, however, like what we really aspire to be able to do if we want a general purpose robot. So like, as we talked about earlier, like the goal for a general purpose robot is going to be able to perform a very wide range of tasks. That includes things like dexterous manipulation, applying forces and moving around in your environment, all those things. So we think we can do moving around in the environment maybe, but we're still not really at the dexterity or manipulation part with it. So this is where where especially better tools seem to be a big trend. So this is from DexWild. So one example is that, like, in this case, this guy is wearing, you can see the camera hat with the Z camera that you can put on your robot. So tracking it and then two of the a glove with basically a pair of cameras on it, so you can always get a good view around the camera. And then you can see him. Let's see, and so now he can do something that's almost natural, but still maybe not super natural, not incredibly natural looking, but a lot better than you would normally get if you're trying to teleoperate this trajectory. And so this is quite a bit faster. This one here. So then another simpler one is DexHumi. So this is a tool, and I like this one because this is particularly a good comparison if you're trying to make the point that I'm trying to make earlier, that that human teleoperation data is incredible. The teleoperation is incredibly slow. So like this is him performing this task with his actual hand of a pair of chopsticks, right? Grabbing something, grabbing a coffee bean and putting it in the cup. Right. It takes him. He's able to get 51 trajectories in 15 minutes. Takes him 5 seconds. Right. And I think he's going pretty slowly there. 7 seconds for using the tool. And if you're doing actual teleoperation, it's much slower, right? And so there's lots of reasons this happens, but one of the big ones is just the latency between the two. So this is something you can somewhat overcome with better engineering, but it's difficult. And there's always going to be some latency and some gap, and there's the controller tuning that maybe you need to get right. Whereas I don't need to worry about that at all. Like I'm just directly moving my hand around, and then I can record exactly what I was doing. And so this generates actually quite high quality data. I figured here. Let's wait. Okay, it should be fine. Okay, so this generates high quality data that lets you do very precise tasks. So in this case, you can see them turning this off, on or off, probably off, given that he's taking it off the heat. And yeah, so still like a bit slower than a person would go. But what we have here is like this is definitely like something that I can bring off the robot. I can record it out now quality data. It is 3 to 5 times faster than it was for us to record it via teleoperation. So it's drastically more scalable. And there's another huge advantage, which is that I don't need to carry the robot around. Because one of the big things that makes a huge difference in all of these policies is the diversity of data that you're putting. And if I have to carry around, and this makes a difference both to policy robustness, to quality, and to performance. So if I end up having to haul this whole robot around with like an industrial robot arm, especially like this thing is UR5, this is dangerous. Like I don't want to bring this into my house. But this you can carry around. No, I mean the one with FRA is obviously the best, but we have to move. So this is generally because it's easier to move around, we get better data, we get more of it, we get the diversity that is so incredibly essential for making these things more general, and it lets it learn. So you don't have to do everything in like one work cell or one data collection one. And finally, I think that there's always simulation. So simulation is a big source of all kinds of data. The big problem with simulation data is that it is very hard to it takes a lot of engineering effort to get a simulation that you can actually use. So what makes it one of a few of the interesting trends that have happened over the year have been better tools. There of course are better tools for simulation, better ways of building simulations using things like Gaussian splatting and pre-rendering to build simulations more easily, but also just the fact that the same co-training logic that applies to the ecosystem video data also probably applies to simulation. So that it is a different task, it's a different modality, but it doesn't need an exact match. I can in fact throw in like data that just kind of like sort of aligns with what we had from the real world. I can train them all together, and it does in fact improve performance. Even like this is a huge difference than quantity of data. But those 14,000 simulation demos are pretty cheap. They're free to me compared to these 200 real demos. They don't take that long to collect, and they certainly don't take the human effort that the real demos do. So it seems like there's a lot of routes that allow us all these things together. Mean that because we can mine data from the different sources, because they all seem to sort of work, and we can scale up data collection, then we should be able to generate them with better tools. We can capture all these information that we couldn't have before in the contact, and that makes it possible to scale robot data using a mixture of methods, which makes it at least a little bit more feasible, but we can start to close the data gap. Maybe it's a little bit of it's at least looking feasible that we can do this, and you can collect data, diverse data in ways that couldn't before. And finally, I want to go into to training general purpose models. So the big trend this year. Okay, let's talk about how robots should think about it. How should a robot reason? How do you reason about solving a problem through physical interaction with things? So traditionally, this would be the job of like a planner, a motion planner, or something like that. This is a symbolic planner. So, like for example, this is a Paxton motion planner from some old work. This is like this robot is going to go and make soup on the stove, and so to be able to get this to work, this is no learning, right? Like, well, there's some learning for object detection, but like what's happening is that it has to detect all these different things. It uses a separate model to generate motion plans, or it uses a separate model to find graphs. It does motion plans. It finds a procedure that works. It goes through this large, heavily scripted set of steps to go and sort of like the symbolic plan. That's like a PDL plan that goes through and does all the manipulation. That tells it what manipulation to conform to get it to this task. And this was I think the instruction here was cook the soup, and so it's told so that's what it did. But okay, so these days though, a lot of what the trend is increasing, instead of having us to define all this stuff via PDDL and setting and like these domain specific languages and generate and write all this stuff by hand, we have these great tools which are these video models or video world models, and Video models are already trained on human data. A video model already knows like what it looks like for you to pour a can of pour something in a soup bowl and make soup. It'll look better than that did. So if we can, so one of the huge trends that we've seen like increasingly accelerating over the last year is people training these models on is people starting to find different ways and creative ways of using video models for generating training data, for getting out of distribution, or for generalizing to new tasks, and for zero-shot execution on a range of different things. So this is from DreamGen from NVIDIA, where you see that where they, in this particular case, they are fine-tuning on robot data, where they're fine-tuning on robot data, and they're able to do things like generate new behaviors, like placing an object, like they're able to watering plants, for example, here, which wasn't in the training data set of the robot at all. But of course, it's seen people watering plants and it's seen the robot, so it can do these things now. And again, some extent, generalize their environments for the same reasons. Okay. These things are more. This thing is fairly preliminary, but there's been a lot of improvement since then. And the other thing I want to note is that there's like sources of video data everywhere. So this is from Counter-Strike, actually. So not robotics at all, but a video game. If you know, right? So this is from Diamond from General Intuition. This though is rendering. Every frame of this is rendered in a world model. So like given sufficient quality of data, these things can actually be incredibly powerful. And we've seen that with like that has been demonstrated by very rapid improvement in these video models over the course of the last year, which has been leveraged to train new agents and to get all kinds of generalizable robot capabilities. Fairly recently, for example, we saw this with this is from 1X Robotics. So we had they fine-tuned their video model with just 500 hours of human data and some amount of robot data. That human data. And they're able to use this to go and do a wide range of different tasks that were not in the robot data distribution. So a relatively small amount of effort of all robot data to be able to get zero-shot generalization to a range of tasks. The way that all these work is through this IBM is an inverse dynamics model. So what that means is once you take the video, you're just training a model that can look at what the robot did and generate what the actions were observed from that video model. This kind of seems kind of backwards in some ways, because you're just basically taking a video and you're turning that into robot actions instead of generating the robot actions in the first place. But it does allow you to leverage these very large amounts of information quickly, and these really incredible quickly improving models. Like the models are getting so much better all the time, basically. I did want to say, like, this isn't the only way that we could do reasoning. Another one of the things that really stood out to me over the last year is this is Momact from AI2. So this is like a different version of a robotics reasoning model. So the previous ones, we could do reasoning basically just by generating videos. We can generate lots of videos. One thing that happens here is that you actually roll out like 5 or 10 videos and choose the best one and then execute it, right? They don't just pick one. So there is actually reasoning happening here in a way, right? It's choosing the best possible instantiation of the world that it can imagine and then turning that into robot action. And this is actually important for success. But it's still 2D video rendered, right? It's not exactly what a robot does a lot of the time. So if you do like the old slow motion planning kind of stuff that we did in the past, like, so robots do need to reason about spatial geometry, object avoidance, and so on. And so here, what this model does is that this is a reasoning model which is a VLA trained to also produce depth tokens. It can use that, and it can also use this to predict trajectories in space. And that means that we can what we can do is we can see it do things like figure out exactly how it should interact with these objects. It gets better performance than the other models. But so by building in these priors, I think that this is one thing that has been very underexplored, at least at the sort of industry scale, the large model scale, is like how do we use depth and spatial information and make robots actually reason over them. But the big takeaways from this part, at least, are I think that world models and video models they allow for a level of generalization that we haven't seen before. They allow us to use more types of data. They allow us to introduce things like a pre-trained phase that didn't exist before. That the more similar to what like how large model training works outside of academic labs. That means that we have things which understand like motion and video and semantics already that you can start to use for robotics. Uh, Learning how to there's a lot of stuff here. We also we don't have a good answer yet for how to do reasoning with robots, like how to figure things through the consequences of the robot's actions. But there's a lot of exciting stuff in this direction. Particularly like video models provide an obvious way of thinking about reasoning. So does world models generating different possible worlds, imagining different futures, generating like spatial context. And I think that this is particularly like something that is exciting because reasoning has always been extremely important for robotics, because like to be able to get generalization, to get error recovery, like this kind of planning seems to be extremely important. It's important certainly for every kind of AI we've seen, and it's always been important for robotics historically to be able to do planning if you want to have anything that generalizes. So, so a few takeaways from this from like basically the last period of research. I think I went through this faster than so we'll have time for questions. But like, so given all that, we still have this issue where it's incredibly hard to tell like which of these things is really working. So like we have some examples like Roverino, which I know Clear contributed to, which lets evaluators all over the world kind of test out different open language policies and run experiments in the little trade. So because there's this generalist policy pool, you can test them out, and that gives us at least some kind of like external validation that these policies are kind of actually working the way that they expected. Because there's so many ways that all of those things that I showed in these previous slides can be just cherry picked, because everyone's testing on a different robot, and everyone's testing on a different environment, and everyone's testing on different data, and the data and all those things make much more difference than any individual choice that you make in a robot architecture, especially once you get out of like your particular lab. Right. So the other nice thing about this is that we've seen like over the last year there before like I would say last year, there wasn't really a common hardware platform for robotics research. Now there pretty clearly is, and it's the users you want. But there's other ones too. Like there's like the Aloha, for example, and the M-arms that they also seen in the robotics lab here. But so the fact that there are a few of these, and none of them are nearly as expensive. So like I said at the beginning of the talk, like when I was in grad school, like the KUKA arm that we used was about $70,000, right? And the UR arm that we had was about $40,000. So like with the Gerbers. So like these were like very, very expensive robots. And now like a full set of YAM arms is 10,000. And Unitree is even the whole Humanoid is less than the KUKA was. So we have robots that are, so because of this, that means that it's much more common for people to be able to have and share code and actually test things out, which I think is very exciting. And it means that there's more pressure to actually open source your code. So I do think in the end, I think the best evaluation and stuff like this, which is going to be testing things on testing other people's code on your hardware and running experiments. But we still, like, honestly, like this is something that we really need better ideas on, because I think that going through all of these, it's been pretty overwhelming to try to figure out which things are actually working. And there's this nice example from MomoAct, which is where this is like the only place that I've ever seen someone actually do like a really long list and an intense evaluation of all of the different types of VLAs. And this is just VLAs, and just big ones too, like because there's about 10,000 these come out every month. But like there are but like you can see like these metrics are bizarre. Like they're just visual matching. Like it's not like success rate. I mean, they tried very hard. They put a ton of work into getting this table together. And so this is just included as an illustration of just like this doesn't tell me a lot, to be honest. Like think like how we can at 81% visual matching, like the images were within this distance to each other. But it's still useful, right? And I guess like I would really like to be able to do better than this. It would be really nice to have an actual success rate table, or something more like a leaderboard like you have on LMSys for an AI model or like an LLM. So if anyone knows how to solve that, that'd be great. The other thing that we have is that this stuff is really slow. So like if you look through the early section of this presentation, or the sort of middle section where we're talking about perceptive manipulation, like you'll see almost everything has like 2x or up to 10x or something speed up, right? Everything is incredibly slow. Part of this is telling out everything is still, even the ones that don't even though things that don't require teleop data are still largely using it. And like the teleop data is always going to be slow because there's latency between the teleop. There's always going to be a bit of latency between the teleoperator and the robot. There's like just the general like the mismatch of controls and application of force is not very easy to specify. So it makes it really difficult to collect good, fast data that is as intuitive as person does. And then we get up to all these hacks. We get things like the gloves and UMI tools and so on. And those get you something that I shouldn't call them hacks because they work pretty well. But like they're not the actual on robot data. And they do allow you to go faster. But even those, like you still have to get like the tracking has to work right. Like for one of these replicas, I need to know exactly where it is in space, and that means that I need to, and all of that makes it really difficult to have robots execute at human-like speeds when they're doing anything that actually involves interacting with the world. And that's not great if you want to try to make money building robots, for example, which I assume at least some of you will want to do at some point. So that's great. The final thing is that reliability, like the big thing that we care about, like outside of the research lab, is like kind of get these things to actually like provide value. Like how do I make a robot that actually can do something? Like if I asked it to do the dishes, I don't want it to do 70% of the dishes and break the remaining 30%, or get stuck in a corner and have me kind of invent it. It should actually be able to do its job. And so like this is something where towards the end of last year, I think we really started to see lots of like tastes on this picking up. And here's the manipulation, although it's always static arms like this, which does make things a little bit easier. But like this is from RL100, which was a paper that came out last fall. But like this, you'll see this, and again, this is actually almost 1x, so you can get a picture of how for the slowness argument I was just talking about. But this is successful box folding. But basically, so the way, but to get high levels of reliability, it seems that you need the combination of like quality data, quality robot, quality everything, quality control, as well as being able to do on robot reinforcement learning like this to be able to perform these really long, complex tasks. And this is autonomous. This is an RL policy that they show like 50 of these in a row, which I'm not going to make you all sit through. But like it is successful. You can take a look at it later. So like I said, there's a lot of progress on this, not on mobile robots, on a lot of different environments yet. The last thing that I do want to note is that when robots, it's a bit weird that like this is a lot of this stuff is pulled from the podcast that I do. Why would I'm still surprised that anyone even listens to podcasts, to be honest. But like this one, but in particular, I want to know. So when I was like, I think that like particularly the social media, like keeping up with things seems so much more important than it was like 5 or 10 years ago. I see some skepticism over there, but like there's but that makes it and that makes like the signal to noise ratio even worse, which makes all these evaluation questions that I'm talking about so much more important, because it's so much harder to tell like from a cool video. We've now gotten very good as a community at building all these cool videos, and it's extremely hard for me to tell which one of those represents actual progress just from watching the video or from even reading the paper all the time. So finally, I think I went through this slightly faster, but that's okay. And a little 20 minutes, so 15 for questions. But my predictions were there are going to be a whole ton of video model papers this year, particularly video prediction world models and all that. This just seems to work really well, and especially with things like there's new video models dropping every day that do incredibly good stuff. We've been seeing one trend that's super positive is that there have been lots more open data sets releasing. This is partly because there are all these different companies that are selling data, and they put data out there. So maybe it's all garbage. I don't think some of it'll be good. But there's like tens of thousands of hours of video data out there now that you can use. So like a lot of these scaling problems, you can kind of start to look at them. Once you have money, you can also buy data from people and collect. Being able to do experiments that we never could have done 2 years ago, right? Or even early last year now, because of all this data being out there. And like I said earlier, like I'm very happy that there are some common robot platforms I was kind of hoping it'd be the Hello Robot, but it's not. But we have the G1, like there's robots like the M-Arm, like people, the fact that people are using the same hardware, that the hardware's gotten cheaper, means that like it's more feasible. And also importantly, that a lot of them have cameras mounted to them in specific locations. This is important because that was one of the huge reasons why you can't like easily transfer across different lab setups, because all the sensing is different, right? So but these common platforms make it easier to share insights. They make it easier to share code, and they make it a lot easier. And so I think that hopefully we'll continue to see that. I think there'll be a lot of more cool robots coming out that'll make your life easier.
你得用
Well,
敲门是吧？
and there's a lot of background dexterity and hands this year. So like people are like hands and mobile manipulation. So like being able to do dexterous tasks, like there's like tactile sensing may be important in this. So there's a lot of there's a video for this behind to get people to kind of develop really dexterous skills for robots. So and I think that this started at the end of last year, like I said, but like this trend towards reliability and people showing like this insanely long takes of robot video, where we get like 16 hours of laundry folding or making coffee or something like that. Like, I mean, it sounds silly and kind of boring, but it is actually great because it shows that it's like, if you're gonna try to show from a single video that your method works, running it for 16 hours is a pretty good way, actually. And like especially if you're like randomly resetting it, or if it's done in a laundromat. Like I think Weave Robotics has the robots operating in a laundromat in San Francisco all the time, right? Like, so you can just walk by and the lighting changes. Like these kinds of things do make it like more clear that this does in fact actually kind of start to work, right? It's found they're not just making stuff up. And so those are the things that I really expect to see a lot of this year. World models, data, and dexterity, and law videos. So like I said, I think it finished about a bit early, but hopefully I want to thank everybody who has talked to me about robotics over the last year. It's fun to come and visit and talk to you all this year. And I hope that this wasn't a total waste of everyone's time where I just talked about other people's papers the whole time, because I haven't done research in too long. So let me know if there's any questions, and thanks.
Why do you think video world models are pushing the success of these policies? And because does it tie back into actual good data for like towards back to telling operated data in that regime, or is it just because you get to see a wider variety of data? Or
I think that well, I'm not sure that they're pushing success rates. Let me be clear about that. I've seen that, but like but I think they're pushing like zero shot generalization, and I think it's because they get to like the advantage of them is that you get to pre-train all human data on a very large set of human data, and that they have all these like kind of all this prior information about the world, about like what a cup is and how one picks up a mug, and all that gets coded in. So that's what I think the value comes from. Yeah.
I feel like when humans learn how to generalize, we have all this other data like touch data, orientation data. What do you think about that as a?
I mean, I think that kind of data is really important to get. Also, I think that there is this is probably the big worry with all these video models to me, right? Is that they're not like they don't capture this very well. But I think that's why I think that I went over the DexEme and the Dex kind of tools. Like I think those do allow you to capture a lot of this contact information in a more complete way. There's retargeting. There's to get the joint states and other information, so you can So I think it's important. I think that a lot of this stuff is this goes back to the evaluation thing, where it's just very hard to tell how much any individual thing contributes to any final success rate. But I fully expect it to be really crucial.
I'm Hunter. Thank you for your talk. I kind of want to get a little bit more information on what you think are some of the challenges of taking egocentric data from, like, let's say, a meta ray bands, and like converting that over into like data for your robot.
So I think this actually comes back to like his question about the tactile. Like the meta ray bands don't have a very wide field of view. They don't capture. So like the ego Emma that I started with, that one's there in that area, which has like it has slam and pose, like very good pose. And even then, it's not quite good enough, and they do post processing later to extract the like Meta does in the cloud. This is just the way that those glasses work. So like there's lots of things that are actually just missing if you want to try to get the Ray-Ban data to be useful. So this why it ends up comes back to I think why people are so excited about like the egocentric data and world models, because like that's something that you definitely can just directly supervise from your Ray-Ban glasses, right? Like and then you end up putting that into co-training, but it's still like it's stages removed from robot data, in my opinion. Yeah. Good. Yeah, I should have put that one in here. Yes, but like so there's a there's been a few things like GS World and Polaris where you use just basically use a video camera and you walk around the room and you can capture like maybe you take a minute or 5 minutes of video data and you reconstruct a scene. Right. So now the nice thing is that I can do a simulation in that Gaussian splatted simulation environment. I can break it up into different articulated objects. I can scan the objects separately. So I have this rigid mesh, which I've gotten just from a couple seconds of scanning with my phone. And then I take these objects and then I can put them in a scene. And now I have a quasi photorealistic scene, right? Like the lighting is fixed and not quite right, kind of baked in by accident. It's not perfect, but it's a lot closer than you get if you just try to put a bunch of object permanents into like Isaac, right? Or Majoko. And so you end up with something that has, at least on a visual level and only a visual level, which is a huge limitation, a really strong correlation with the real world performance. So yeah, does that make sense?
Yeah, so the faster that doing is meant.
Yeah, because the one of the big problems with simulation engineering is just that it takes so long to build scenes. It takes like a lot of effort. Like it can take like 6 months or so to set up a particular task. So like anything that makes that process faster and more automated saves you a tremendous amount of time. And like so like it's a similar argument to like the tool baiting, right? It's like if I walk into a room, if I can just like walk in a room and scan it with my phone or pick up a bunch of objects with a pair of funny grippers, then I can get data diversity really fast. Right, and data diversity makes a tremendous difference if I want to try to build a generalist robot, right? That I know that like someone else can try out in a different lab. So, I can go first.
Thanks, Chris, for a great talk. Like on the evaluation part, I have to say that our Robo is a good practice, and I'll work what's going on to a possibility. But it's very painful to like manually roll out 100 trials like in one day. Yeah. Like so, I wonder like if you think like other approach, for example, like real-time, or like word model or like offline metrics to be a more scalable version, or like what actually bottlenecks each approach, and what may be a like ultimate way that we can like unlock evaluation for everyone. I know it's very hard for me to just hear thoughts.
Yeah. Yeah, I think it's a good question because I don't have a good answer on evaluation. I don't think anyone does because I think it's been like one of these perennial issues for robotics research forever. Like that evaluation has just always kind of been terrible for robotics. But like the problems with simulation and with world models. So like world models are used for evaluation. Like there's and so are simulations, right? Like especially for internal evaluations, world models are great. We talked about like the 1X stuff that I mentioned. They started out actually doing this for evaluation. Because the nice thing is you can like take a scene. If you have a world model, even if it just fits your environments, you can then roll it out and you can see like if I do something different, I can very easily test it without creating this full articulated environment of the world, simulation of the world. So like, but the problem is that a general purpose world model is really tough, and a really true general purpose world model is probably also a general purpose policy, like we see with the video models, right? So like it gets kind of circular and difficult, I think. And the same problem that like simulation goes back to his question, it's your name, but like the where like currently simulation is just really hard to do, like getting simulations that are high fidelity and accurate and aligned, and they're getting better. And like I think the boring kind of hand wavy answer is that they'll probably need like there's room for all of these, but like right now like as simulations get better, they will get with more fidelity, more accuracy, better contact physics. Like we will start to see the gap decreasing, and maybe one day we will be able to get rid of remover in that.
Thanks for coming. I'm curious, beyond the home, what do you see as the most promising place for your well deployment and why?
That's a good question. I mean, I think lots of in the place that they're getting deployed a lot right now is like in industry and manufacturing and logistics and moving objects around. I think like the nice thing about those environments is that they are relatively controlled compared to homes. Like the downside, of course, is that people actually want things from the robots and on schedule, and so things have to work a little bit better and work faster. But yeah, that's the kind of word. Of course, I think there's the last mile is another one. Like I think carrying packages to people's doors, that'll be a big one.
So I have a question back to evaluation. So I agree with you that if you do it very well, then it's sufficient. You can use it to improve.
Yeah.
But it's very easy to do it wrong, such that then you over optimize. You end up optimizing the wrong objectives. So overfit into pick and place this and that. So my questions. So I agree it's sufficient, but do you think it's necessary?
Evaluation.
Can we go ahead in this robotics roadmap that you showed without evaluation? And we know that this is part, at least in generative model, this was the case.
Yeah.
Where there is no clear evaluation, no clear metric, human that say this image looks good, this image doesn't look good.
Yeah, I mean, this is a good point that maybe we really don't need. I think that from the reason that evaluation is important is because we are trying to, like, if I'm trying to choose models or make decisions on what I'm going to train next, it's nice to have some more concrete information. The other thing is that there are two types of evaluations, and one of them is useful and important and the internal evaluations. Like, am I improving on my own environments and my own checkpoints? Like that's the one that maybe is like the most solid, because I do know that my own environment gives me that my own evaluations do something, but they don't tell me anything about, like, if there's some new model coming in that I could potentially just sort of train. Yeah. So I think it is fair. Like, ultimately, I think it'll just be testing. Like, I think that with generative AI with like the generation, I think that, like, I think it's a good point that there was never really any good benchmarks for like video data or whatever, but also people were able to, like, third parties are able to test them, right? Like, so like, I think that this comes back to like the maybe the robot arena or just like download a model kind of stuff. Like, I need to be able to test it then to be able to see which ones are where we're actually making progress, I guess. That's harder with robots. And that's why we end up seeing like such a kind of jagged or confusing impression in the field, because like, if I get to choose what I share and I only share this one thing and there's never a product that gets released, it's very hard to get a signal. Maybe that's a personal frustration.
If like I'm going now this question, like what if like VLA become the paradigm or like similar form factor, like then you can like when you can do offline metrics to see like whether you improve and it's getting better, like internally saying like because like
开个会怎么办？走我房间吧。
So
But my question is,
so in the top, yeah. So
so when we observe like high zero, we will see that many cases he just override a certain like prompt.
Yeah.
So you will see that it only has two patterns. One work, the other not work at all.
Yeah.
So maybe like in the future, like if everyone follows similar like paradigm, like a VLA, like vision then reaction.
Yeah.
But kind of like wipe check like the reactivity of policy, and this can be like divided into like offline matrix. So you can use like maybe offline to test the uncertainty in certain decision making, or like maybe other like progress rate or jerkiness, etc. Do you think that's feasible? Like for
like, can you be offline metrics? Like,
like the strictly defined like input and output form, and you having some like specific thing that is you are able to measure some like crossing the policy more like
Yeah.
Yeah, and you see how much can you steer it.
Yeah, like how it is basically like how a distribution of the inputs.
Yes.
Yeah. I feel like this would be an extremely valuable thing to have, I think, because like right now, so much of the issue with data is trying to identify what's with like robot data collection, getting these policies work in general. It's just getting like how a distribution is the scene, how much more data do I need here, right? Like, I think that would be even maybe the more useful thing than just evaluation, but I think they're closely related.
I think it's very hard for you to find what is in distribution nowadays. Right?
Yeah, but
Especially with the correlation pattern.
Yeah. Well, it's just a measure of uncertainty. Like, I guess do you have the model output some uncertainty? Like, how is it? Is that the yeah?
Going into 2026, are you thinking about what data operations and modalities you keep in-house versus outsourcing certain?
I don't have a good answer for that. I think like the robot data collection is still something of an art. I don't think anyone really has a good answer for that yet, to be honest. Maybe some people do. But yeah, it's something you've got to get an intuition for, I guess. Like whether or not they generate good data. Yeah.
I'm wondering why you think robot inference is so slow, and if we could use like LM inference or serving techniques to make it faster, or is the model completely different?
I unfortunately don't think we can use LLM kind of tricks to make it faster, because a lot of those tricks are not going to work on a robot, right? Like we have to like the robot, we're using much smaller amounts of data of memory. We're using it locally. Like we're not going to set it up to the cloud where we can use a lot of the big optimizations that they use. It's slow because the policies are big in part, and the execution is slow because the data is slow too, right? The data is actually slow, and you see that with like a lot of these clips. Even when the guy is doing it with his hand, he can't help but being slow in that one. Yeah. So unfortunately, it's like a whole bunch of all the above things that are wrong with it. And
Just to pick up on, I think, Antonio's question. I mean, one thing you said about social media. Okay, so I think just like to give some advice, if you have advice for people. So, we don't trust evaluations in papers.
Yeah.
There's lots of noise, and there's social media. So how do people decide like what to pay attention to? Because I think you're quite good at this, right? And also, how do people go about using social media to their advantage? Again, something you're quite good at.
I appreciate that. I don't know. I mean, I think that unfortunately I don't have a good answer other than like spending a lot of time on it. It's like a separate skill. Like that's not a good answer at all. Like it's just yeah, I wouldn't actually recommend my approach. It's not very scalable. But I think that when it comes to social media, I think that it is like it's social. There is a community. There's people out there who I think whose opinions I tend to trust, right? And that is like a strong signal. And this is like part of it is that there are people who spend more time on it than you, who are who can maybe hopefully provide some signal, or do like you can like I should take a look at this. This person actually read the paper. I should read it again. And like I have personally found it very useful to like. Part of the reason why like I've liked doing a podcast is because I get to actually have an excuse to talk to everybody one-on-one, and that like once you actually are talking to someone, it's much easier to tease out like, wait, hang on, that didn't make sense. What is it? And then and you can learn kind of what's working and what isn't. So that's not really a great answer, to be honest. I'm sorry, but yeah.
Yeah, I'm a lot involved, like gosh, my book like words them. But I'm not even touch the name, not just like the hand and that like another part. So how do like bridge data things?
Yeah, like how do we bridge the different data sets between like egocentric data versus like tactile data or whatever? The reaction in different parts. Yeah. So I think that one of the ways that you can think about bridging these data sets is to co-train it, like mix it all together in the training process, and make sure that the actual how the data ends up is well represented. Like that you're not just like drumming it out with egocentric figure data. So once you have that, then you can start to get good amount of information. Then you can start to train things that it tends to learn shared representations, and it tends to so this is like when it comes to things like the tool data, that you can do some amount of retargeting for like where the hands are and figure out what the skeletons are. In general, I think a lot of it's also pipelined. like for training large models, like 1x in particular is a good example. Like where you start with pre-training, they pre-train on like the model is WAN, so it's pre-trained on like a massive amount of human video data, third person. Then they do mid-training, so like the AI models do, and train it on concentric data, and they train it on there's only data. So like it's a much more like it's a full engineering process, right? It's not just like a simple rule, unfortunately, I think.
What would you say in terms of like a lot of processes? It seems like, especially for something like a Dream like one that you had up there with like the VLM generating new possible scenes. Like, how do you see the market kind of like taking those types of algorithms that seem to be very sequential and then bringing them to reactive robots so that they can they can dream stuff up, but you don't have to wait 5 minutes to give it a new command.
Well, so I mean, NVIDIA came out with a solution for you like a couple days ago with their Dream Zero, like buy a bigger GPU. No, I think we'll be able to make like some amount of it will be distillation. Like we can generate a bunch of these in parallel and like just train on the ones that work and try to train smaller models. And I think that we're at least when it comes to like those kinds of tricks from the bigger AI community, like the LLM video people, like I think the surface has barely even been scratched. Like we don't generally like have quantized models that work for robotics, right? So I think there'll be lots of things that we could do to speed up performance, hopefully.
All right, guys, we have to end the seminar right now. And thanks, Chris, again.